All right, for this video, I want to talk about radiation pressure. So let's look at some equations. In particular, there's a lot of letter P's in this stuff, and I wanted to clarify some of the letters before we do any math. Okay, light has no mass. However, it does carry momentum. Now, this may confuse you. You might be thinking, oh, I thought momentum was mv. Well, for light, here's the equation we can use. So the momentum of a photon is going to use little p for momentum, right? And that's going to be the energy of that photon divided by the speed of light. All right. Conceptually, if this helps you kind of see it, think about our old school equation for kinetic energy where you did have mass. We'd have 1/2 mv squared, and you could think of momentum as mv. If you rewrite kinetic energy, we'd see it was p squared over 2m. So if you wanted to think about regular particles as having momentum, they would be p squared over twice their mass. For photons, I guess you could think, I guess there's this other relationship between momentum and energy. All right, so there was always one before, it's just maybe a little bit different now. Now, here are the two equations in which we might use for the energy of a photon, hf or hc over lambda. Well, if we look at this one, we could see that this ends up being some constant and 1 over the wavelength. So we see that the momentum of a photon is inversely proportional to its wavelength. Okay, that's cool. Now, what about intensity? Intensity is power over area. You're going to see me use a script P for power, right? And to be clear, remember that power is energy over time. So intensity is energy per area per unit time, if you want to think about that. So it relates to the energy of how many photons are going through a unit area in a given time. So, all right. Now, in addition, we're going to use pressure, which is big P. So we've got little p, script P, and now big P. Pressure is force over area. Now, I hope you can see that there's got to be some kind of connection between these things, right? So, for example, if it helps you remember this is 1 over area. Well, force is dp dt, and I'm ignoring the vector nature of these right now, so I apologize. I should probably be saying force is the change in momentum vector here. And so you might be saying, well, what's the direction? Well, the direction the photon is traveling tells you the direction of this momentum here. So this equation is for the magnitude of the momentum, but the direction is the direction it travels. So in theory, this upper equation should relate to the lower equation, right? If you know the momentum of a photon, that should relate to a pressure, or basically to a force, all right? So that's a big deal. Furthermore, we could see that the momentum probably relates to the intensity because it relates to the energy as well. So all three of these are related. Now, if I could, I'm going to try and make this, and there's a lot of letter P's there. I want to try and bring this up. Let me see if I can go to, all right. The idea here is I've got a laser beam somewhere across the room, right? And it should be bouncing off this piece of metal, all right. Now, this isn't going to be a perfect demonstration, but I'll try and put some chalk dust here, and maybe you'll be able to see the beam coming in, but you probably can't see the beam coming out. This aluminum foil creates a very diffuse reflection, it turns out, but you might be able to see the beam coming in right here, coming right in. Well, there it is. You can kind of see it traveling in right there. So the idea here, what are we talking about? We're saying the photons in this light beam are exerting a force on this mirror as it reflects the light. And we see, now, if you think about how a balloon is inflated, right? All the little air molecules bump into the wall of the balloon, and they create enough pressure to keep the balloon from collapsing in on itself. Similarly, all the little photons in this laser beam are producing a tiny amount of force each time they reflect. And that's basically what we're trying to talk about in these equations over here, right? You could find the momentum of each little photon that's in a laser beam, and it corresponds directly to the wavelength. So if you know the wavelength and you know the intensity of the beam, well, if you know the intensity of the laser beam, that tells you something about the number of photons hitting per second. And from that, you could move on and figure out the force, because we'd have the momentum of each, and we could know the number from this equation. And from that, you could get the total force by adding up all of these. So that's kind of an interesting result. The practical application is the solar sail. So maybe what we could do is work through a problem and kind of look at this one. Let me see where I want to go with this one. So I'm looking at 33.14 on page 228. Let's go over to here. All right. And so the idea here is we've got a solar sail. Oh, so what did I say? 33.14. So imagine we just have a big piece of aluminum foil floating in space. Let's just keep it easy. All right. Now, the idea here, you could imagine a photon. I'm going to draw a photon as like a little bullet shape with a wave inside of it. It's coming in this way, right? And we know the momentum of this photon is h over its wavelength. Well, when it hits that, it's going to reflect. And if we assume it comes off with the same wavelength here, the momentum leaving is also h over the wavelength. But if we think of these as vectors, this first one was going in the I hat, this second one is going in the negative I hat. The change in momentum is 2h over lambda, right? Or you could say it's 2 the energy of the photon divided by c. That was the other way to write it. So we see that that's the origin of the force, right? There's a change in momentum. Okay, well, from this, we know that the change in momentum of the spaceship, how about we say the sail, should be equal but opposite to the change in momentum of the photon, right? So what we see is there's a change in momentum of the sail, which corresponds to, and in this case, I should be careful. I made a mistake. This was a change in momentum. This had a direction associated with it. This was negative I hat, right? It went from plus h over lambda in the I hat to negative h over lambda. So that's why it's 2 in the negative I hat. So this one would then be positive 2h over lambda in the I hat. Great. So that is the origin of the force. If you shine light on a sail, it's going to either absorb the light and get pushed forward because it absorbed that momentum, or reflect the light and gain twice as much momentum. All right. So that's kind of the basic principles of this. All right. Do I want to say more on that? Gosh, I'm tired. Sorry, I'm a little tired. What else do I want to do? Well, I guess we could try and keep going on this one and see what we see here. All right. So, and just to that end, let's try and get the force involved here. So force, if we look at our equations on page 225, we see that the force is equal to twice the average intensity times the area all over C. Okay. Now, if you recall, you might be saying, wait, I didn't see that in our equations a minute ago. Hold on, let me do this really quick. The idea is, over here, I mentioned that all these equations should be related. Now, you could read a textbook and get to this, but I'm trying to get through this one example problem. The fact remains here is that we see that the force, which we just described as being related to this change in momentum, right, does relate to these other things. And we can see that time factors into there and the intensity. So ultimately, the energy is the connection that connects that in there. All right, so moral of the story, I'm going to use this equation here. All right, back to that board. Well, I know intensity equals power over area. So the idea, if this is the sun, I can expect these waves are going to spread out. Now, keep in mind, these are not plane waves. These are spherical waves. All right. The light from the sun is spreading out spherically. And I could, give me just a sec. You could think of the sun as being like this, right? And it's emitting light spherically. So the idea is at some larger radius, the energy's maybe out at this radius and it's moving outward spherically. So it's sort of like the sun's energy is traveling out in these infinitely larger beach balls, right? Now, at some point, way out here, you've got your solar sail. Far from the sun, right? And this is where it gets a little bit tricky. Over here, the area is something like 4 pi r squared, right? The area over which the sun's energy spreads out is 4 pi r squared, where r is your distance from the sun. So the intensity of the sun would be the sun's power output over 4 pi r squared, where r is however far you are from the sun. Now, what gets different here, if you can imagine this, right? So the idea is the sun is spreading out energy over this huge piece. Well, if I just look at one spot here, oh my gosh, right? Oh, this is getting kind of crazy. But if I just look at one spot, one tiny piece of this, and maybe just so I can hold this, let me use this. So let's say this is our solar sail. The idea is, from the solar sail's perspective, it's hitting it perfectly, right? It's hitting it almost at a right angle. And from the solar sail's perspective, you can actually treat the light from the sun as a plane wave. When you get far enough away from the center of the sphere, if you're a small object, right, the waves appear to be coming in plane waves, even though they were emitted from a spherical source. So at the location of the solar sail, we can actually think of the area as just being the area of the sail. So over here, the area is just s squared, where this is some square of side s. So the power absorbed, this is power, should equal area of the sail times the intensity of the sunlight. As a result, we get this very unusual looking equation, right? The intensity of the sunlight is power of the sun divided by 4 pi r squared. Oops. Where this is distance from sun. All right? Take a second to take that in. The idea is if you take the area of your collector, or whatever's absorbing the radiation, times the intensity of the source at that position. So if I get the intensity here times the area here, I get the power that I'm absorbing, right? Now, in this case, because it's reflecting, we get a factor of 2 for reflecting, right? You're reflecting this light, so we should get twice as much energy imparted, all right, or twice as much momentum imparted. So out of all this, we're going to get some kind of crazy equation that looks something like 2 s squared power of the sun divided by 4 pi r squared. In short, there's some sort of constant times 1 over r squared. We see that as this spaceship gets farther and farther away from the sun, right, the sun's power doesn't change, but the sun's intensity does. As you get farther from the sun, it gets weaker, right? The intensity diminishes in proportional to r squared. All right, so that's what this equation up here is talking about a little bit, right? So there's a factor of 2, there's a factor of area, and then there's this intensity, which is this power of the sun. All right, so again, this factor of 2 was from the reflectivity. If perfectly reflecting. Right, so in this case, we saw that we would get 2 s squared, that's the area of the sail, right? And then in this case, there's a c here to convert this to, right? It's because over here we were talking about power. It turns out to convert this from, maybe you remember this old equation, power equals force dot v. Maybe that makes sense. So you can see that power divided by speed should have units of force. So that's basically, we took the power and divided it by speed, so we have units of force. And then what did we get here? We said it was the power of the sun, and then it was over 4 pi r squared. All right, so that's the force that's pushing this thing away. Well, there's also gravity pulling it back in. All right, so out of all this, I need some more room. I need some more room. Since this is written up in your notes as well, I'm not too worried that you can't read it there as well. Sorry, I'm erasing on you. Here's the, now, if we think about this sail, right, there's a force outwards from radiation. That's this one. There's a force back towards the sun. That's going to be GMM over r squared. And we know that the force radiation hopefully is going to be larger, otherwise this wouldn't work. Minus GMM over r squared should equal mass times the acceleration. If I plug in this stuff, hopefully I'm not screwing up something, but again, you got the solutions. If I made a typo here, I apologize. I'm just going to put this one thing in red. Clearly, this gives us some sort of limit on the size of the sail you would need, right? The power of the sun is some known quantity. We could figure that out. These are constants. We know the mass of the, and in this case, I should be clear, this is the mass of the sun, right? So I'm assuming this is a spaceship far from Earth trying to travel outwards. We're ignoring, right? So let's just assume for a minute it's only the sun and the solar sail here, right? So the idea is, imagine this piece of aluminum is sitting out in deep space, all right? And it's just, that's it. And there's the sun, and the sun is shining on it, and it's reflecting this light, which pushes it outwards. And the idea here is, if this term is bigger than that term, you could actually accelerate away from the sun, and that would be some sort of the physics of how a solar sail works. There's obviously more to it. Now, and again, the point I keep stressing is, this factor of 2 is for reflective, right? If it just absorbed the sun, like let's say if you just put a black cloth out here in space, like say this, right? This is not going to reflect the light, it will absorb it. You'll still get some momentum, but you'll get half as much because it's not reflecting the light, right? So I think that's probably all I need to say on that one. There might be a few more details you can clean up, but these are the important parts of this problem, right? There's 2 forces, gravitational attraction. And, you know, you could talk about the size of meteorites and things now, right? You could imagine like different sized meteorites might settle into different locations based off their size and reflectivity. That's kind of interesting to think about. Anyways, that's enough on that.